Assalamu alaikum class, how are you? Go fine. Let us start with our today's topic, the artificial satellite. Most probably this might be the last topic of this chapter number 5, right? And hope you have learned a lot from your previous lesson. And inshallah, for the question and answer session, we'll see you there on the Zoom. Now, the artificial satellite, before telling you something about the artificial satellite, I just want to tell you that what is satellite? Satellites, a satellite is in fact an object that revolve around a planet. Is called what? That is called a satellite. Now, there are two different kinds of satellites. One we call the natural satellite. One we call the natural satellite, and the other we call the artificial satellite. This difference is important. For example, what are the natural satellites? Few examples, let us talk about it. For example, all planets they move around the sun. They are the natural satellite. Why? Because they orbit or move around the sun. So there are natural satellites, right? Moon around the earth. Moon is the example of the natural satellite. Now, what are the artificial satellites? Artificial satellites are in fact the man-made satellites, behind which is a big team of engineers and scientists, right? And they have a different purpose. Artificial satellite, there are a lot of examples. For example, International Space Station, they are the Hubble telescope, I would like to tell you. They are the kind of artificial satellite. Now, what are the purpose of the artificial satellites? There are, first let me tell you, there are two kinds of even the artificial satellites. Those two kinds of artificial satellites are, one we call the geostationary satellites. The geostationary satellites. One we call the LPOs satellite, LPOs, the low polar orbit satellites. The geostationary satellites are in fact the kind of satellites that revolves around the Earth equator wise. For example, let us see if this is Earth, as you see, this is our Earth, for example. Then what could be, this is the radius of the Earth, for example. Then what could be the geostationary satellite? So those geostationary satellites, they will move around the Earth in this way, for example, because you know all these motions are anti-clockwise. This is why I've chosen it like this. So, like this, right? So if I just put it this kind of symbol like this, for example, let me mark it like this, as you see. For example, let us see if this could be a kind of satellite as it moves, right? This could be any satellite. I call this satellite as the geostationary satellite, right? So if it moves around the Earth equator wise like this, so we call this kind of satellite as the geostationary satellite. The LPOs, the low polar satellite, we will not discuss it right here now because this might be beyond the scope of our syllabus. but they moves around the Earth pole-wise, and usually such kind of satellites are used for scanning the Earth weather, right? And those satellites are usually the LPO satellite. There are four important applications of the artificial satellites. The important application of the artificial satellite, the first one, all the satellites, they are used for what? For communication. For communication purpose. Right? This is how, for example, today you see me, the lecture which I'm just, this online lecture which I'm recording for you is possible because of what? Because of this communication satellites. There are communication satellites, right, which help us in communicating with the rest of the world. So today, for example, you know that we can live without all the thing, but not with the internet, right? It is all because of what? All because of the artificial satellite. The artificial satellite help us in communication. You know, the communication is not just this one, it's television, radio, and all means of communication, right? So the satellite help us in the communication. The second one, it is used for weather forecasting, right? Now, whenever you are leaving your home, right, then first you see your weather updates, whether you should go out or not. Nowadays even you can have the weather forecast for 24 hours, for 3 days, for 1 week, for 15 days. So it is all because of the artificial satellites. They help us in weather forecasting. So to monitor the weather, we use artificial satellite, and when you just Google this weather satellites, then you can learn even more about it. And the third one is for space exploration, for research and space exploration, right? How you know about the rest of the planets, or about the universe, and about the stars, the black holes, the planets, the Milky Way, the galaxy? It is much more are actually coming from what? From those artificial satellites, right? Why? Because those satellites, like the Hubble telescope, I will give you one kind of example, right? They are just placed outside the Earth atmosphere for the clear view and the clear pictures, right? And they gain much more useful information, right, about our space. So that is one of the reasons that artificial satellites are used for what much in the astrophysics, for the research in space exploration. Another important point is for the military purposes, right? And that is what I would like to. They are used for example, for spying purpose. So it is those kind of satellites are usually operated by the military or the advanced military. For example, the United States of America, Russia, and maybe the Great Britain, French. They all have this kind of system where they just see the world, what is going there, and they can use this for just detecting the military movements, right? They used the spying satellites for just finding that whether there are some nuclear reactors, where there are some nuclear reactors are going to build or not, like that. For example, to detect the launching of the missile from certain territory. So they are what? They are all spying satellites. So there could be a lot of other uses and applications, but I think these four enough for you. So we can use artificial satellite for communication. Is now I'm communicating and the artificial satellite is helping me to reach to you. So for weather, for example, when you get up early in the morning, first you just see that how the weather is today at your place, and the next one for research and space exploration, and then for spine. So these are the four few important points. Now the first question here is how to place the given satellite into its orbit. That is a very difficult job, and on what factors that really depends. Right? First of all, I'm supposed to tell you about the geostationary satellite. What are geostationary satellites? Geostationary satellites are usually the kind of satellites which always stays at the same point on the Earth. Geostationary satellite have the relative velocity with respect to the Earth is zero. Right? It means the Earth completes one round trip around its own axis over 24 hours. So the same is the speed of the geostationary satellite also. The geostationary satellites completes one round trip around the Earth in 24 hours. Right? So it always stays the same point. Why? Because to communicate with that particular station. For example, if here is the United States of America, if there is, for example, the uplink and downlink for a certain satellite installed here, then it moves the alternate, this moves system to this also moves. So it always points on the same point on the Earth, right? So those kind of satellites are usually geostationary satellites, and they are usually at the altitude of 42,300 kilometers from the surface of the Earth, right? So they are the geostationary satellite. This is why they are called geostationary. Geo means Earth, stationary means stationary at rest, which appears to be at rest relative to the Earth, right? So those are the geostationary satellites. Now we just want to calculate the orbital speed of the satellite. The orbital speed of the satellite. What is the orbital speed of the satellite we orbit? The orbital speed of the satellite, it is the minimum speed required to place the given satellite into its orbit, rather so that it's neither far onto the Earth nor it escape into the space, and always stay in its orbit, known as orbit of the satellite. So what could be the required speed, the required initial speed given to the satellite to place it into its orbit? Right, for this purpose, we would like to start from what? To start from the equation of what? Centripetal force. Why? Now let us see, for example, let us consider a satellite, right, which is supposed to be placed at a height h above the surface of the Earth. Let this be the velocity of the satellite. I label this as the orbital velocity, the orbital. Right? Definitely this entire distance, you just see I'll mark it as this is the radius of the orbit. And I would like to mark this radius of the orbit as, if this is the radius of the Earth, so the radius of the orbit, small r I would like to write, radius of the orbit, r naught, this will be equal to definitely r plus h. R plus h. This is what? This is the radius of what? This is the radius of the orbit. Now plus you know that when the satellite moves around the Earth, you see that its direction is constantly changing. This speed, the orbital speed, It is constant in magnitude. It is what? Constant in magnitude, but you see that this is what? This is continuously changing its direction. So you know that when there is a circular motion, there must be centripetal force acting on the satellite. And that centripetal force job is to constantly pull on the satellite towards the center of this Earth. This is the centripetal force, right? So the required centripetal force that acts on the satellite could be what? You just see, look, as from the centripetal force equation, what I can write, the necessary centripetal force that will act on the satellite, it will be equal to what? Mass of the satellite. Sorry, I have forgotten, I should mention the mass of the satellite. This is satellite of mass n, which moves around the Earth in an orbit r plus h with a speed v naught. Right? So you see this centripetal force that acts on the satellite, it will be m v square, which v square is v naught. Right? Into what? Into the radius of the orbit. And what is that radius of the orbit? That is r naught. This is my equation number 1. Now class, you know that there must be some agency, there must be some source which can provide the centripetal force. So when you whirl something around, for example, you tie it to a rope or string and you move it around a circular orbit, the centripetal force will be provided by what? By the tension in a string. So you see there is no string, right, in between our satellite and the Earth. Now, do you know where does this centripetal force comes from? What is the agency they provide this required are the necessary centripetal force, right, which provide this necessary centripetal force to keep the satellite moving around a circular track. Right? This perpendicular force, this centripetal force, it will be definitely provided by the gravitational force. Right? Now, what will be the gravitational force? This centripetal force Fc, it must be provided by what? It must be provided by the gravitational force that acts on the satellite. Now the question is, what gravitational force? How? Look class, in order to that gravitational force, this centripetal force, right, which is equal to the gravitational force that will be equal to the weight of the satellite, but not on the surface of the Earth. It will be equal to what? The weight of the satellite, not this weight on the surface of the Earth. The weight of the satellite at that height, at that particular altitude, at that very particular altitude. If you just simply write m into g, you will make a mistake. So this centripetal force Fc is, which I told, Ft, they will be equal to what? M into g, right? But what they m into g? Rather gh, the value of g at that particular height, right? So you see that, look, now this is my equation number what? This is my equation number 2. Now if I just compare 1 and 2, since the left equal, then the right will also be equal. So you see, look, what I will be writing, this mv naught square by r naught into what? Into mgh, right? This m will get cancelled with this m, right? And what I will be writing here is this v naught, since there is a square, so let write it like this. This GH into what? Into R naught square root. This is the minimum velocity that is needed or required to place the satellite in the given orbit, so that the satellite neither falls onto the earth nor it escapes into what? Into the space. Any velocity greater than this value will take the satellite into the space, right? Any velocity less than this will cause the satellite to fall onto the earth, right? Now, if you just see, look at this equation. This V naught will be equal to what? It will be equal to GH into what? It will be equal to GH into R, radius of the earth, plus what? H. Enter the root. Now, there are a few important points which I want to discuss with you. And you see, they look, what is the first point? The first point is the orbital speed of the satellite. It does not depend on the mass of the satellite. You see, do you see any factor like that of what? Like of mass? Of course no. So it does not depend on the mass of the satellite, one thing. But if you have a satellite of 1 kilogram and if you have a satellite of 1 ton, for example, and if you place it into the same orbit, the orbital speed must be the same. But remember one important thing, that to place 1 ton satellite into that particular orbit, you will need more energy in placing 1 kilogram or 10 kilogram of satellite into that orbit. Why? Because to give that you need more energy there. Why? Because that is massive. So to produce that acceleration, you will be needing more force, more energy. So for the bigger velocity, for the bigger satellites, more energy will be needed to place it in that orbit, and for the smaller mass satellites, less energy will be needed. But they don't depend on the mass. The orbital velocity doesn't depend on the mass. Now let us see what could be the minimum velocity. For example, look at this equation. If the satellite is very close to the earth, like for example, if the satellite is so close to the earth, if I just take this height 0, right, the satellite fall very close to the earth, then what will happen to the orbital velocity? This orbital velocity near the surface of the earth, then for example, if the satellite is very close to the earth, then what will happen? Look, what is going to happen? This GH will become equal to what? This GH will become equal to this R naught, for example, this equation. This will imply that R naught will become what? R naught will become R, radius of the earth, as you see. And what will happen? And that is, of course, now we don't have GH because the satellite is brought closer to the earth. And this GH will be equal to the value of G at the earth. So this equation will now become what? As you see, look. So this equation V naught will now become equal to what? G into R E under the root. Now the rest I am giving upon you. Then if you just put the value of this, it will be around about 9.8 meter per second square, 6.4 into 10 to the power 6 meter, and then I think this will came out to be, I think let me figure out the value to you. That came out to be 29,000 kilometer per hour. Right? So when you just place both those values, then you will calculate it either in kilometer per hour or like that. Okay? So this is all about the orbital velocity. Let me wind up my today lecture. As in this lecture I told you about the artificial satellites. right, about the satellites. Satellites are the objects that revolves around the planets. Then I told you there are two kinds of satellite: the natural satellite and the artificial satellite. Natural satellites are those for satellites. For example, Moon is a natural satellite for the Earth because you see Moon moves around the Earth in its orbit. Artificial satellites are usually the man-made satellites. Then I told you the implication of satellites, the artificial satellites. I told you artificial satellites are used for broad purposes. I told you it is used for communication purpose, and it is used for there is for weather forecasting. It is used for research and space exploration, and it is used for spying purpose. Then the important point was to how to place the given satellite into its orbit, and that was to calculate it to the speed of the orbital speed of the satellite. And that orbital speed of the satellite can be found by using these equations. And then I told you we should start from the centripetal force equation, and then we must know the agency that provide the centripetal force, and of course this agency is the gravitational force that acts on the satellite at that very particular height. And then we have found what could be the gravitational force, and that would be equal to the weight of the satellite at that point, right? And then we equate these two equations. We came across this equation, and the most important point which we have learned, that the orbital speed of the satellite is mass independent. It does not depend on the mass, but remember I told you that if you have a heavier satellite or lighter satellite, the only difference is the amount of energy. If you want to place a heavy satellite into the orbit, you will need more energy. If you want to place a light satellite into the orbit, the energy required will be less. But if they both have the same orbit, then the orbital speed must be the same. And for the a low altitude satellite, for example, low altitude satellite means that which is very much close to the Earth's surface, then we just ignore h, and then we came across this equation, and the value could be calculated as I told you, 29,000 km per like that. So that could be the required speed, orbital speed for the satellite, the minimum required. So okay, thank you very much.